Hi, everyone. It's a real pleasure to be here, and I'd like to thank the organizers, as so many before me have. My title here is about comparing optical clocks in a coherent way, and I'll get to that a little bit later, but I'd like to point out that ICAP has always been a nice combination of precision measurements such as you get with individual isolated trapped ions and many-body physics, as we've heard a lot about this morning, for example. And sometimes it might seem like there's a bit of a dichotomy here, where it's Montague's versus the Capulets situation. But what I hope to convince you of during this talk is that we can really kind of marry the merits of many-body physics and isolation and precision available with trapped ions. So the work I'm going to tell you about is all at NIST in Boulder, Colorado. I work in the ion storage group. And I'll tell you about some optical clocks based on aluminum ions. I'll really briefly mention a new project that we're starting to build optical clocks based on thorium nuclear transitions. And it'll come in three parts, my talk. So first I want to tell you about these aluminum ion clocks. So as I think we are all familiar with here, optical clocks really are an atomic oscillator with a laser whose frequency is stabilized to the atom. And then some output, which might be a microwave signal that's obtained by dividing the optical frequency down with a comb. And I just want you to keep in mind this picture because I'll come back to this picture and modify it later. At NIST, in my group, we really like aluminum ions for optical clocks, and that's because of this clock transition here between the singlet S0 ground state and the triplet P0 excited state. This is a good transition because it's very long-lived. It has that 20-second lifetime, so we can do narrow line with spectroscopy. It's also really insensitive to the environment. So for example, the black body radiation shift at room temperature is a few times 10 to the minus 18. But there is a challenge with aluminum, and that is that the lowest electric dipole transition is in the vacuum ultraviolet at 167 nanometers. So we don't have this laser. Instead, we're using techniques from quantum information where we co-trap an aluminum ion here in the same trap with a logic ion that will be either magnesium or calcium for the clocks I'll talk about today. And because these two ions are both positively charged, their motion is strongly coupled, and we can laser cool the magnesium in order to cool the motion of both ions. And furthermore, we can use these motional modes, which are quantum degrees of freedom, to read out the internal state of aluminum. And that's using a technique called quantum logic spectroscopy. So in this technique, we have the aluminum ion. We have this quantized motional mode. It's a harmonic oscillator. And then we have our logic ion here, and I'm showing magnesium. So the way this works is that we first start in some unknown superposition state of the two clock levels of aluminum. We attempt to drive a motional sideband transition on this logic transition of aluminum, which adds a phonon of motion if and only if the the aluminum ion started in the ground state. And then we can map that phonon of motion onto the magnesium qubit transition here and read this out with standard fluorescence techniques. So with this quantum logic spectroscopy, we've been building aluminum clocks for over a decade now. And we're able to do narrow line with spectroscopy like this. But I want to emphasize that this is a very general technique, and it's pretty powerful. We've other groups, so Pete Schmidt's group at PTB has done quantum logic spectroscopy of highly charged ions using a different logic ion. In the ion storage group, we've done quantum logic spectroscopy of molecules, which don't have cycling transitions, again with a different logic ion here. Okay, but that's not really what I want to talk about. I want to talk about aluminum clocks, and in particular, I'll focus a little bit on this third generation aluminum clock we've had at NIST. And this was largely built up by a fantastic then postdoc Sam Brewer, who's now a professor at CSU. In this clock, we evaluated the systematic uncertainty, and I won't go through all of these in detail, but what I want to point out is that the total uncertainty here is slightly below 10 to the minus 18. It's limited by these two terms here, which are both second-order Doppler shifts. These are actually things that we've been working on improving already in our fourth generation clock. But with the third generation clock, we had this systematic uncertainty down here. So this is the systematic uncertainty of a handful of state-of-the-art optical clocks over the years. And we're sitting down here just below 10 to the minus 18. And this really reminds me of this statement by Deimelt, where he first proposed that we could build these optical clocks based on single ions, that's what he called mono-ion oscillators, and achieve this 10 to the minus 18 fractional inaccuracy. So it took us a while to get there, but I'm going to go on record to say we can still improve further, as long as you have facial hair like Deimelt. More seriously, what do we want to do with these clocks? Well, we want to do metrology for the SI second, as Helen talked about, or we want to do fundamental physics, like Eckert-Pike and others have talked about. And all of those involve comparing different clocks. So if I add comparisons, frequency comparisons to this plot, you'll see that the accuracy of comparisons have lagged behind the accuracy of clocks by an order of magnitude. And since all three of these clocks are in Boulder, we set out to try to do better frequency ratio measurements. I don't have time to talk about the details, but this is a really big effort. It's involved a lot of people. And so I want to acknowledge my collaborators here, the ytterbium lattice clock run by Andrew Ludlow and the strontium lattice clock run by Jun Yi, as well as the combs used for these comparisons run by Tara Fortier. And so with all these people, we have a lot of grad students, and grad students are always hungry, so we've named this the Bacon Collaboration. Okay, so what have we actually done? Well, we've measured frequency ratios, and so here I'll show you just a few results. So this is the stability of the measured ratios as a function of averaging time. And you can see here we have two ratios on top of each other involving aluminum with either lattice clock. The stability there is limited by quantum projection noise of the single aluminum ion. We have this other line down here, and that's the frequency ratio stability between the two lattice clocks. And there we have better quantum projection noise because the lattice clocks run with thousands of atoms. In any case, we've averaged these down for a few tens of hours and come to total uncertainties in the ratio measurements down here, slightly below 10 to the minus 17. So these are now, to the best of my knowledge, the best known fundamental constants of nature, although they're not that interesting of fundamental constants. So let's talk about what we can do with these sorts of ratios. Well, we can do things like search for ultralight scalar dark matter, and this was already mentioned by Eckert-Pike. I'm going to go fast. We can try to constrain the coupling of this ultralight dark matter to standard model particles. So this is the coupling constant. This is the mass of the dark matter particle, and if we had this coherent ultralight dark matter, it would cause oscillations in these measured frequency ratios. So because we don't see oscillations, we can put constraints. And so this is actually an old constraint from Berkeley a dozen years ago. We went back and reanalyzed some data we had at NIST from mercury and aluminum clocks and improved these constraints slightly. The new measurements I just talked about between aluminum and the lattice clocks come in actually around the same constraint level, and they don't do better than previously because the sensitivity of the transitions we have is lower than it was for mercury in particular. So you'll notice there's a lot of white space in this plot, and where should I expect to see a signal if dark matter really is this ultralight scalar dark matter? Well, you can go to the literature, and when I did that, I found one candidate talked about in this paper up here called the relaxion, where naturalist constraints exist. These are if you want to also solve some other problems in fundamental physics with the relaxion, it has to be in this range. And so what are we going to do here? This is a problem. We can either improve the stability of these frequency ratio measurements, or we can use atomic or molecular or nuclear transitions with much higher sensitivity. And in particular, in my group, we've started to work on this thorium nuclear transition where, because of the higher sensitivity to apparent changes in the value of the fine structure constant, we kind of automatically win many orders of magnitude here. So this experiment is just being started to be built. I have a project with Mariana Safronova and one of her grad students, Hani Zahir, looking at how we can use dynamical decoupling to extend the frequency sensitivity, or the bandwidth, up to higher frequencies, which corresponds to higher dark matter particle masses. And a nice thing about thorium, although I'm not going to say anything more about it in this talk, a nice thing is that because it's very insensitive to its neighbors and it has direct readout transitions, it's possible to imagine building a many-ion clock. Okay, so let's get back to the main story, though. We're at this point with our aluminum clocks where we want to do better in stability, and we can think about trying to do that in a few different ways. One is maybe we should just jam some more aluminum ions in our trap, average down with the number of particles, and we've started to try that. So this is work led by Dave Hume, in which we pack in an equal number of aluminum ions and magnesium ions. We've gone up to 4 aluminum plus 4 magnesium. And now the problem is that we want to do this quantum logic readout because we don't have the direct readout transition. But we can't do the same sort of simple emotional sideband transition we were using before. So instead, we've borrowed a page from some other experiments at NIST, these sensitive force detection experiments that John Bollinger talked about, in which we can apply an optical dipole force, this coherent drive force, I'm calling it here, to the aluminum ions in a way that it's only felt by aluminum ions in the ground state. So we can drive coherent motion in this ion crystal where the amplitude of the motion is proportional to the number of ground state aluminum. We can read out that motion using this geometric phase gate type scheme in which we prepare a cat state, a motional cat state of magnesium. We apply this spin-dependent force, and then we close this interferometer. And so with this, we've been able to read out, well, one, more efficiently, so we can read out a single ion faster. But probably more importantly, we've been able to read out more than one aluminum ion. So here's a picture where I'm showing these different fluorescence levels from the magnesium ions that correspond to, well, 2 aluminum ions in the ground state, 1 aluminum ion in the ground state, and 0 aluminum ions in the ground state. And this is a scan over the line with these 2 aluminum plus 2 magnesium. Okay. I want to turn now, though, so we can maybe imagine with that multi-aluminum quantum logic readout going up to 10 aluminum ions. But what if we want to go to much larger effective number of ions? Well, we've been playing or thinking about a few different techniques for doing so. And the first is something that we're calling differential spectroscopy. And this is a technique specifically for comparing two optical clocks in which laser phase noise is made to be common mode so that it drops out. And in that way, we can extend the Ramsey free precession time to minimize the quantum projection noise. So here, this Ramsey free evolution time, big T, can be extended out to the excited state lifetime of aluminum, that 20 seconds I mentioned earlier. Okay, so this is kind of the typical picture of clock operation, where you do some Ramsey spectroscopy and you measure this transition probability that depends on the detuning between the atomic transition and the laser frequency. The frequency ratio measurements that I talked about earlier were what I call incoherent ratio measurements, where we just have two completely independent clocks. We beat both clocks with a frequency comb and come up with some ratio. And in that case, the stability of the measurement just is the combined instabilities of the two clocks. But what I want to talk about here is this different technique, differential spectroscopy, in which we use the same laser, by which I mean two lasers phase locked to a comb, to probe the two clocks. We probe them simultaneously such that the phase noise seen by clock number 2 is the frequency ratio times the phase noise seen by clock number 1 in any given probe. And then we try to estimate the difference in phase offset from the comb for the two clocks. And one way to do that, so you can look at a few different ways to do that in this paper up here, but one way that we've used experimentally is to compare our ytterbium lattice clock in Andrew Ludlow's group with our aluminum ion clock just down the hall from each other, where we, with ytterbium, cut the Ramsey interrogation short, measure the phase of the laser, feed forward to the laser being used for Ramsey interrogation of aluminum the frequency ratio times the measured phase. And because the frequency of aluminum is a bit over 2 times the frequency of the ytterbium lattice clock, although this time is within the laser coherence time for ytterbium, it is not within the laser coherence time for aluminum. So that would give us a factor of 2 in interrogation time, but we can go further. We can use both ytterbium lattice clocks in zero dead time operation, measure the phase here and then here with the other atomic ensemble, and keep going and apply this sum of measured phases in the ytterbium clocks times the frequency ratio to the aluminum probe laser, and have an aluminum probe that's equal to n times the probe length of the ytterbium lattice. Okay, so that's the idea. Here are some results. What we're doing is still Ramsey spectroscopy, so we're measuring some Ramsey fringe shown here. And at a Ramsey interrogation time of a few hundred milliseconds for a single ytterbium probe per aluminum probe, if we don't do this phase feed forward, we get a contrast here in gray, and if we do the phase feed forward, we recover the contrast of Ramsey interferometry. Similarly, if we go out to, well, here is 10 ytterbium probes per 1 aluminum probe at a probe time of 4 seconds, we also have this coherence. And this is coherence between 2 different atomic species at a probe time of 4 seconds. And that's really incredible to me that we can do that. It's, I guess, a real testament to the hard work that's gone into developing frequency combs and phase stabilization techniques to connect different ensembles. Okay, but let's turn that into a clock comparison. We can do this sort of repetitive synchronized Ramsey interrogation. And this is a comparison between the aluminum and ytterbium clock, where we achieve this couple 10 to the minus 16 per root tau stability. And you could compare that with this 1 10 to the minus 15 per root tau stability that we achieved with our incoherent technique that I mentioned at the beginning of the talk. So we've improved by almost an order of magnitude. To put that in context, here are the very best frequency ratio measurements between different species clocks, and I want to be clear about that. I'm not including comparisons between two clocks based on the same species. Where the very best stability achieved is, in fact, this work here, where we've gotten this ratio measurement stability of a couple 10 to the minus 16 per root tau. Okay, so that's one way to kind of combine single ion clocks with many body physics, where we basically borrow the low quantum projection noise of the lattice clock. But can we scale more directly? Can we use more and more ions in a clock? And I want to spend my last couple of minutes talking about that. So one way to do it would be to borrow some of the techniques that have been developed for quantum computing with trapped ions, this kind of QCCD architecture. And if we have a lot of individually controlled ions, we can start to think about doing measurement algorithms that are a bit more complicated than just applying the same Ramsey sequence to all of the ions simultaneously. So can we do better in clock stability if we have individual control of all of the atoms or ions? The answer is yes. So here again is this clock stability, the standard quantum limit. And if I go to my information theory friends and ask them, how much information do I get? They tell me that I get log n bits of information about the phase difference between the atoms and the laser per interrogation. Even if I go to entangled states, I still only get log n bits of information, right? That's not actually that much of an improvement. I win by a factor of 2. In contrast, if I just think about classical measurements, let's go back to the 16th century. If I want to measure the weight of something, what do? I have this pendulum sort of balance. I put a big weight on, and the big weight is heavier than my test weight, so I get 1 bit of information. And I put a bit smaller weight on, and I get another bit of information, and I keep going. And look at this. I get 6 bits of information by doing 6 measurements. And you might think that's only a classical thing, right? Can we do that in quantum mechanics? And the answer is yes. In fact, it's the basis of the factoring algorithm. Shor's factoring algorithm is this quantum Fourier transform algorithm, in which we want to measure the phase that this gate applies. And I won't talk about the details, but we do some algorithm where out pops on individual ions the successive bits of that phase. So I would love to be able to transform this phase estimation algorithm directly to the problem of clocks. I haven't quite figured out how to do that yet, but I can do a simpler thing. And imagine that I have different ensembles of ions or atoms. I take one set of those atoms or ions, and I probe them at one probe time in this zero dead time configuration, like the differential spectroscopy I talked about. And I take another set of atoms or ions, and I probe them at a longer probe time. And now, in just the same way as we did for this zero dead time differential spectroscopy, we can estimate the phase using these shorter probe time ensembles to extend the probe time beyond the laser coherence time for these longer probe time ensembles. And so here you can see that the stability we've gotten by doubling the number of atoms is twice as good. It's not square root of 2 better, as for the shorter probe time ensemble. So we can extend this further. We could keep adding ensembles, and every ensemble we add would have the stability. That's an exponential scaling of the stability with atom number. Or equivalently, it's like gaining proportional to n bits of information about the phase per probe. Okay, this is something that we've started to think about and experimentally in collaboration with Sandia National Labs. They're building these ion traps that look a lot like this original quantum CCD architecture. But I also want to point out that there's some really nice work at PTB. This is the group of Tanja Mechtabler building arrays of ensembles of ions. You could also do the same sort of thing with Szymon Kokowicz's multi-ensemble lattice clock, or with Adam Kaufman or Manuel Andre's tweezer clocks. So I think this is a really exciting area to pursue in the future. Okay, so I'm actually going to skip the last thing I was going to talk about here and just go to the conclusion. When we want to do metrology or fundamental physics, or really anything with these atomic clocks, there are these two important metrics, right? There's the instability with which you can measure things, and there's the accuracy, how well can we average down in the end. And these are existing clocks and existing demonstrated frequency ratio measurements. So, so these three clocks were used in the Bacon result I showed. These two clocks in the filled points are this differential spectroscopy comparison. But it should be possible to do better. So I mentioned scaling up the number of aluminum ions, and in principle, we might be able to get somewhere like here with that. I mentioned these QCCD clocks with ytterbium or other ion species for that matter. And we might be able to get somewhere like here. The thorium that I mentioned is here, and then the thing I just skipped is an idea to build many ion clocks based on large Coulomb crystals with tin. And some of the nice things here are that this tin in particular is really sensitive for fifth force searches. And with thorium, we could do really sensitive dark matter searches. Okay, so I'm going to stop there. Thanks for all of your attention.
Okay, time for questions. Okay, Bill first.
So I'm not sure I've understood correctly this exponential scaling. So maybe you could go back to that slide. It sounds too good to be true.
Yeah, of course there are caveats, and I can talk about them.
Okay, so but you're actually saying that there would be an exponential scaling in the stability with atom number.
Yeah.
Okay, so why how can that be?
Yeah. Okay, so one, I want to point out this was talked about or first proposed near simultaneously in ion storage, but also by Anders Sorensen. And both of these are good papers to look at if you want more information. But the basic idea is just that we're extending the Ramsey free evolution time. And in practice, of course, there's a limit to how far you can extend that, right? In order to kind of keep going to lower and lower instability, we'd be going to higher and higher probe times. And I don't know what the practical limit to that is. There's a fundamental limit from the excited state lifetime, right? And so aluminum is actually not that good for this because we're already able to probe near the excited state lifetime with these differential techniques. Ytterbium ions don't really have that problem, or the tin ions I briefly mentioned.
But it sounds like that should just scale linearly with Ramsey time. Where does the exponential come
The exponential comes in because the Ramsey probe time is scaling exponentially with the number of atoms.
Okay, I'll have to think about that one.
Okay.
Because like in this example, I'm just going up by a factor of 4 every new ensemble I add.
More questions? From
Because I have more questions.
no, you're next after for other people. Yeah. Any question from students? Students? We encourage students to ask questions. Remember the prize. And I pick up the prize from Bill. Bill prepared for us. Reward, yeah. Anyway, I think there's an online, right? Online question. Huh? Okay. Instead of having a lower bound, can we put an upper bound on the cooling, on the coupling constants? This way, one might be able to have a finite range of the coupling constant. That makes sense?
So let me just pop up that slide. I think that I might have been unclear. So these are upper bounds on the maximum possible value, experimentally consistent possible value of the coupling constant. Right, and then the question maybe was asking if there is a lower limit here to how far we might possibly have to search. And I have to defer to particle physicists there because I don't know. In this particular case, there is a statement that it doesn't make sense to search any lower than this, although I recognize that's quite a bit lower than we can search, at least currently. But there are new ideas all the time, so I really am excited about the future of these sorts of searches.
The other one over there.
So, Dave, I'm curious about your CCD architecture, where you place different ions, presumably in different traps and so on.
Mm-hmm.
Do you see fundamental or practical limitations how such a delocalized over many traps clocks would perform compared to what you mostly have now, single trap clocks?
Yeah, so that's a great question. I think there are a lot of technical challenges. And one that I've been thinking about currently is just with these surface electrode traps, which I imagine might be the way to go. You have large RF currents running around to create the confinement, and that creates large ACB fields at the positions of the ions. And this is something that I didn't talk about at all, but like for aluminum and for all of the top performer ion clocks out there, we use these big traps in part, and big and symmetric traps, in part to avoid ACB fields at the position of the ion. So that's one. You have to do careful RF engineering. I think you could maybe avoid that by going like the Tanya Meshtabler route with these larger traps. But I think you have kind of a lot of the same problems as the quantum computing folks, the trapped ion quantum computing folks. And so I think there's a nice synergy there where we can really take advantage of the very nice fabrication that's been developed for quantum information.
Thank you.
Maybe, Bill, we have 1 minute. Have a quick question. Yeah.
Right. So in the experiments where you used both ytterbium and the aluminum ions, should I think of that as using the ytterbium as a kind of a flywheel for the aluminum, or should I think of it as a technique for getting rid of the Dicke effect, or is it the same thing?
It's both. It gets, like, because of the synchronous interrogation, we do get rid of the Dicke effect. But there's also this flywheel thing going on where we're probing at beyond the laser coherence time for aluminum. And the only reason we can do that is that our phase reference is not the laser, it's the ytterbium atoms.
Okay, so you're doing both. So just on the ytterbium, the interleaving gets rid of the Dicke effect, and then this sort of better ytterbium clock is a flywheel for the for the aluminum clock.
Yeah, that's right. But
Yeah.
there is one kind of subtle distinction here. It's not that the ytterbium is stabilizing the laser, because you can't do that fast enough. Feedback
Yeah.
doesn't work. It has to be feed forward.
Yeah.
And so in that sense, it's really just a differential phase measurement. We're not actually making the laser that good.
Yeah, but it has that same flavor of
Yeah, that's right.
of being a flywheel.
Yes.
Right. Gotcha.
Yeah, and that is the limit. I mean, just talking about limits, right? Like, could we keep going if we had an ion with a longer excited state lifetime? The limit would be we can't possibly do better than the quantum projection noise for the lattice clock.
Okay, I have a quick question. All those searches for physics beyond a standard model are actually model dependent. You have something in your Hamiltonian, then you got shift in. So if they are like many models, you're going to do it one by one again. I mean, model can have many. I mean,
Yeah, I mean,
that baffled me for so many years. I mean, right? Theorists can give a model, and we can do calculation to change Hamiltonian, right? The energy shift, then you search, then you got zero.
yeah. So
Basically, right?
so that's right.
How to understand it? How to understand this kind of thing? I mean.
Yeah. So
I mean, this is the work is perfect. Okay, I don't argue with the experiment details from theoretical serious point of view. I mean,
yeah. So I really like the sort of EDM constraint plots where you can see clearly
yeah,
that by looking for the EDM, you're able to constrain a lot of different possible theories, right?
Yeah.
And similarly here, although I've only put one model of dark matter up, any of these models of dark matter that can couple to the standard model in various ways would also show up on this same plot and be constrained by the same experiments. So I have this kind of standing challenge, and this isn't the right audience, but I would love to add more models of dark matter to this plot, and I'm just waiting for particle theorists to tell me where naturalness constraints put them.
Okay. Yeah, we have to start by thanking David again.